This conference will now be recorded.
So, good evening. Today we'll be discussing about torque, turning effect, torque and turning effect, rotational equilibrium, principle of moment, and angular momentum. So, these are the topics which are coming under this rotational motion part. So far we have discussed what is called rigid body, what is center of mass, etc. We have discussed. We have discussed the equations of motion for center of mass in the last class, and we have discussed the motion of center of mass. So today we'll see the turning effect or torque. So if you remember in the last class, what we have, like in the beginning of this chapter, we had discussed how many types of motion a rigid body can have. So rigid body can have purely translational motion or purely rotational motion, okay, separately, like individually. Or if a rigid body is not fixed at any point or about any line, then a rigid body can have combined motion of rotation and translation. But if a body is fixed at any point or along any line, then the body has only rotational motion. Okay, and see, today we'll see what is this torque or what is turning effect when a body is moving in a straight line, or when a particular body has a translational motion. Force is responsible for the translational motion. So for translational motion, force is required, or force is the governing agency of the translational motion. But what is the analog of force in case of rotational motion? In other words, what is actually governing the rotational motion? Motion means there will be some force involved. So in case of translational motion, that is the external force which is responsible for translational motion. But in case of rotational motion, that is the torque which actually is responsible for rotational motion. Okay, that is the torque. So torque is rotational analog of force. So the analog of force in rotation is torque. Okay, torque. So what is this torque doing? Look, let me tell you what is turning effect at the same time. So turning effect is actually called, the moment of the turning effect is called torque. Okay, or in fact you can say turning effect is called torque. So you look here, this is a door. When opening a door or closing a door, what we do, we apply the force at the edge, okay, or the handle is actually fixed at the edge, as you see here. This is the handle. Okay, handle. We apply force over there to open and close. Okay, and if we apply force here, will you be able to open the door at the hinge where the door is fixed? So the door is actually fixed with these two hinges, and the door is rotating about the line which is passing through this hinge. Okay, so which is called axis of rotation. So here axis of rotation, suppose we want to rotate something, if we apply a force just near to the axis of rotation, see this, if we apply a force here or here, it will be little difficult to, so at least if we apply force on the axis or near the axis, it is not possible to rotate at all. Okay, but if we apply force little far, then there will be difficulty. Suppose at the middle, if you apply force and just push it, it will be little difficult, or pull it, it will be difficult to open or close. But when we apply the force at the end, or the near the edge of this door where the handle is situated, so the effect of this force is more, and it can rotate the door easily. Okay, it can rotate the door easily. So the larger is the force, see there are two things: where you apply the force and how much force you apply. There are two things in this case. So this effect is called, this rotation, this we are just defining as turning effect. Turning effect, and this turning effect is more effective if the force applied little far from the axis of rotation. In a sense, far from the axis of rotation. So turning effect actually depends on two factors. One is the magnitude of the force, how much you apply, and the perpendicular distance of the line of action. See, line of action of the force is suppose this one. This is the line of action of the force. Okay. So what is the perpendicular distance from here with this? So you have to find out the perpendicular distance from this. Okay. Suppose here the perpendicular distance is d and the applied force is this. So you'll see F into d, this factor, this along, see this force, magnitude of the force and the perpendicular distance from the axis of the rotation. Okay, this is, these are two factors on which the turning effect depends. If we apply very near, then see d is much less, right? So that effect, turning effect will be not that great. If we apply it in the middle, maybe little greater effect you will see. But if you apply here, you see this product F into D will be maximum. So what is D? D is the perpendicular distance of the line of action of force from the axis of rotation. Okay, as you see here. So during this rotation, you know what happens when you apply a force, because the door is actually hinged at this particular positions here. Suppose A and B at these two positions, the door is hinged. So this hinges also will try to hold it up. Okay, and apply a force in the opposite direction. So because it is fixed it here, this is fixed here at these two hinges. When you apply a force on the door at the handle, there will be a force exactly equal to this applied force. This is applied force, suppose, equal amount of force, but it will be acting in the opposite direction, whereas their line of action of these two forces will be parallel to each other. Line of action of forces will be parallel to each other. Okay, so these two forces actually are involved in this rotation or turning effect. So these pair of forces are called, they are equal and opposite, but they are directed in the opposite direction. So their magnitude is equal. Okay, but they are acting in the opposite direction, and their line of action of forces are also not the same. They are actually parallel. See, these are line of action of forces. These are parallel to each other. Okay. So this pair of force is called couple. So these two forces which are, see, if I just draw a bar or beam of rod, okay, beam of iron, and if I apply a force along this way, and the same force, like same equal and opposite force you apply at this, like in the opposite direction. So these two forces are called couple, couple of couple. Okay, these forces are called couple. A pair. So couple means a pair of forces. They have equal magnitude, but their line of action are not the same. Okay, they are oppositely directed, but their line of action is not same. Now see, as we discussed, for rotational motion, torque is responsible. Now we are going to discuss about torque, or we'll define torque. What is torque? So what is torque? Torque is the moment of force. Okay, torque is also termed as turning effect. Turning effect or torque. So torque is actually torque torque is defined as the moment of force, the moment of force. I'll define this with an example what is called. So moment of force is called torque, and it is measured quantitatively. It is measured by the product of either of the either of couple of forces and the perpendicular distance distance perpendicular distance of line of action of force, line of action of force from the axis of rotation. Axis of rotation. So it is measured by the product of either of couple of forces and perpendicular distance of the line of action of the force from the axis of rotation. See, look here in this particular figure, we'll define what is torque. In this particular figure, look, there is a particle P. Okay, it has certain mass m, suppose, and it is rotating about z axis. Okay, it is rotating about z axis, and if I say the z axis is actually passing through the origin, and see the particle is situated at r distance, r vector. So this is r vector. Okay, this is r vector. And the line of action of force, if you see here, this will be, if this is r vector and this, see the position vector, and the force, the force on this particle, acting on this particle, is making an angle. So this is r vector, and this is the force which is acting on this particle is F, which is making an angle theta with the position vector r. Okay. So if this is angle theta, this also will be theta. Okay. Then this distance, this is d, perpendicular distance. How do you get? So d, see r, see this is actually theta. Suppose this is perpendicular to this, like line of action of force. If this is theta, look, you can write easily d by r is equal to sine theta. So d is equal to r sine theta. So this is the perpendicular distance. Okay, I'll just clean this part. I hope you have understood the definitions. I'm just cleaning it because we have to do certain calculation here. Okay, so look, we have defined. See, torque is actually denoted by tau. Okay, it is a vector quantity. We'll see shortly. This is a vector quantity. Okay, this is a vector quantity. Torque is a vector quantity. So torque, let us first write the magnitude itself. Torque is defined as the moment of force, and it is actually of the measure of couple of force. Suppose F is the one of the force of couple. Okay, so F into D, this is actually torque. What is D here? D is R sine theta, as I have shown you here from the figure. So if we write, see, r sine theta, F r sine theta, if we write in terms of vector, what you get? R cross F. Okay, r cross F. So this is actually the definition of, or the mathematical equation of force. So sorry, torque. Torque is actually r cross F. It is denoted by or written as r cross F. So this is the, see, r cross F means moment of force. It is called moment of force. Moment of force. So this force is actually linear force, or the force which is actually external force which is applied, and this force. See, the torque is actually responsible for rotation, not this force alone, not this force. So moment of the force is actually making the rotation. In case of rigid body, when they undergo a rotation, then the underlying factor is that is torque, and torque is re- denoted as r cross F. So r is the position vector here, F is the force applied on this particle. So this is r cross F, or rf, or fr sine theta. So see, we have seen that torque is actually a vector quantity, and it can be expressed as cross product of position vector and the force applied on the particle A, particle P here. Okay, so look, torque is r cross F. Okay, now since it is a vector quantity torque, it has both magnitude and direction. So magnitude may be written as r f sine theta. Okay, but what about the direction? What about the direction? So this direction can be obtained from the thumb rule. See, right hand thumb rule for vector multiplication. You can use that formula. If you have if you have A and B, A cross B, then you have to get C. Okay, so according to right hand thumb rule, if you stretch your all four fingers along the direction of first vector in the cross product R cross F, so this is A, and then curl your fingers around the other vector B. So what you get is C. Your thumb will point the direction of C. This is actually thumb rule, right hand thumb rule. If you stretch your four fingers towards the first vector of the cross product, and if you turn or if you curl around the vector B, second vector, then the result will be the third vector, that is C. Okay. So sometime maybe you will be given R and F. You have to write down the torque. So you can use this right hand thumb rule to give the direction. Okay. Magnitude anyway upon multiplication you will get. Okay, so this is actually the way to find out the direction of the torque. Now what we'll do, so this is very very important when you go in the 12th standard, the torque concept of torque or the direction of torque, how to find out direction of torque will be required. Okay, so fine. Now what we'll do, we'll see torque we have got, see R cross F. If we take the magnitude of this, so what you get RF sine theta. Okay, RF sine theta or FR sine theta, whatever you can write, and you can see sine theta, this factor theta. You have to see that factor. What is this factor? This is the angle between R and F. Okay, R and F. So this term is dimensionless quantity. This term sine theta. Only this part has dimension. So torque has a dimension of work done actually. Okay, work done. Torque has a dimension of work done. So it has, see, R and F, that means it is centimeter, this is F is dyne centimeter or Newton meter, like that. The unit of torque is, so I'll just write it here, unit of torque. Unit of torque is actually, see, it is having the same dimension as work done. So work done has SI unit joule, so we can write torque, SI unit of torque, SI unit of torque. Okay, let me write that. So in SI unit, torque tau is equal to this RF. This actually have, so in SI unit, torque has a dimension of work done. Okay, dimension of work done. Because this is displacement, this is force, so it will be giving joule. Okay, joule. Sometime it will be written as joule also. Sometime it will be written as Newton meter. Sometime it may be written as dyne centimeter also in cbse unit. Okay. Now we'll see how torque work. Like, see, in case of force, linear force, we have seen that work done is equal to force into displacement. This is actually linear displacement force FDS. This is linear displacement, but in this case, so work done by torque. Work done by torque. So what we know? We know, suppose if we have a rigid body, okay, which is actually rotating about this axis, and we'll just consider a particular body here, P. Okay, so this particular body starts rotating, like the particular particle start rotating in this circular path. Okay, circular path. Then you know you have you apply force here, or you have actually linear momentum in this direction. Okay, in fact, let us see the force in this direction, and the angular position, suppose this is theta 1, and when it go here, so it has another angular position, okay, theta 2. So in this case, this is the suppose force in this direction I am taking as force. Okay, here it is. So this is theta 2, and this is the vector, this position vector. And look, this is the this much is the linear distances travel. And let us say this angle theta 2 minus theta 1, suppose this angle is delta theta. So a particle P goes from this particular position to this particular position, okay, and thereby it has angular displacement d theta. Sorry, this is called delta theta. Okay, and we know what is delta theta. Delta theta is the angle. Angle means, suppose this is s is the linear distance. So s by r is equal to delta theta. S by r is equal to delta theta. Okay, so I can find out what is s. S is equal to r delta theta. Now if suppose this force is acting on this particle, so there will be a work done on this. So F into S will be work done. So suppose this is delta W. So F is F alone and R is R delta theta. Okay. So you can see this F into R, this can be written as torque. So torque into delta theta. Now it is going from theta 1 to theta 2. So you can find out the total work done. So total work done will be integration theta 1 to theta 2 delta W, this one. So this is theta 1 to theta 2 tau delta theta. So if you look this, so tau anyway, you have, so if you know this theta 1 and theta 2 and torque and also the angular displacement, so this actually since we are going for integration, let us write in terms of total derivative, total integration. So if you know the torque, if you know the initial and final limit, then you can find out the total work done by the torque. So in in a single line, what is work done by torque is integration theta 1 to theta 2 tau d theta. Okay, this is the work done. Okay, so we'll see what is called power. Power means energy delivered in unit time or per unit second. So suppose here energy delivered is delta W in delta T time is this one, T into delta theta. This is the work done we have seen T into delta theta, tau into delta theta. So this will be the this will be stored as energy. Okay, so if this happens in delta T time, so you divide this with delta T, so this you'll get delta theta by delta T is equal to omega, average angular velocity. So tau into this omega. So see, in case of linear or translational motion, force or like work done was given force into displacement, whereas power was given force into velocity. Force into velocity. So here also you look power, rotational power is equal to torque into the angular velocity. Torque into the angular velocity. Okay. Now we'll learn in an interesting thing. So we have learned already what is called turning effect, etc. Now we'll see principle of moment. So what does this principle of moment say? See, the principle of moment. So you have now learned what is called moment or moment of force. At least what you know is moment of force, which is written as force into displacement. This is nothing but torque also. Okay, this is actually moment of force, moment of linear force, or we say moment of force. That's all. So when a body is rotated, I'm sorry, not rotated. Suppose, okay, let me just draw one thing. So suppose a body is actually pivoted with some fulcrum. Suppose here like this. This is a beam of rod. Okay, this is actually pivoted here. And suppose there are two masses, M1 and another one is M2. They are hanged. Okay, they are hung here. They are hung on either side. Okay, so suppose this distance, this is this is called fulcrum, or sorry, this is the point of pivot. Pivot in the sense, with respect to this point, the beam will try to be in the equilibrium. Okay, let us suppose this distance from this load to this point is having distance d1, and this much has d2 distance. Okay, and this has weight m1g. Look, this is m1g, and this has weight w2 is equal to m2g. Okay, now according to this weight w1 will try to rotate this beam in the anti-clockwise direction, whereas the beam on the right hand side will try to rotate the beam in the right hand direction. Okay, about this pivoted point, suppose P. So about this pivoted point, the beam will be rotated by these two weights. See, this weight 1 will try to rotate the beam in the clockwise direction, whereas the weight W2 will try to rotate the beam in the clockwise direction. So look here, there are two forces with respect to this. This, suppose this is the axis of rotation. Axis of rotation goes through this. Okay. So see, these two masses will try to rotate in along two different directions, right? But when this body will be in rotational equilibrium, that means there will be no rotation. When the body is at a rotational equilibrium, rotational equilibrium, then what? Then the moment anticlockwise, sum of the anticlockwise moment, okay, sum of the anticlockwise moment, anticlockwise moment, will be equal to the sum of clockwise moment. Sum I have written already, summation over clockwise moment. Okay, I'll give you the proper mathematical definition of this thing, or principle of this moment. So what principle of moment is saying that if this particular body is in rotational equilibrium, then clockwise, clockwise momentum, if you take and sum them up, will be exactly equal to the sum of the anticlockwise moment. Or in other word, take sum of clockwise and anticlockwise momentum total. In total, they will give rise to zero. Okay, let us write what is clockwise moment. Clockwise, clockwise, clockwise is this one. Okay, so W2 into W2 is the force. Force into displacement is the moment. Perpendicular distance is d2 here. So this is the moment. And see here, W1 into d1. This is the anticlockwise moment. So this is anticlockwise, and this is clockwise. Okay, clockwise. This is the thing. Now if we just take this, okay, I'll redraw this. W1, and you have here W2. This distance is D1 up to here, and this distance is W2, sorry, D2. So this side it will try to rotate it anti-clockwise, this will try to rotate clockwise, so both the moments are same. Omega 1 D1, so W1 D1 is equal to W2 D2. Okay, so this, see, we can just compare this thing with the lever. We can consider this with the lever. Okay, for any lever action, see, the load into load arm, so you can write this as load into load arm is equal to effort into effort arm, effort into effort arm. Okay, so this is W1 is somewhat like load, and this is the perpendicular distance from the load to the rotational axis. So this load into load arm, this one is the load arm D1. You look this, and this is effort. This WT is effort, and this is effort arm. Okay, now if you want to have mechanical advantage, you have to define mechanical advantage as load overcome by effective, effort applied. So finally you will see it will be effort effort arm by load arm. Okay, load arm is equal to mechanical advantage. Mechanical advantage, MA, mechanical advantage. Okay, so this is actually the moment of force and principle of moment of force. So according to principle of moment of force, when the body is rot in rotational equilibrium, the sum of the anticlockwise moment of force will be equal to the clockwise moment of force. Okay, so I have shown you here how it is at mechanical equilibrium. So this is the thing, and mechanical advantage is defined as the effort arm. It is the ratio of effort arm to the load arm, and effort arm will be always greater than the load arm. So that's why mechanical advantage is always greater than 1. Always greater than 1. Okay. So we'll just see one more thing here today. Then depending on this principle of moment, there will be numerical problem. We'll take up it in the next class. Now we'll learn what is called angular momentum. So in case of translational motion, we have seen linear momentum, which is denoted by P. P is actually mass time velocity, and this is also a vector quantity since velocity is a vector quantity, and this is actually called linear momentum. Linear momentum. Linear momentum. Okay. So this is actually the measure of linear momentum is the measure of the translational motion. How much it is measured, like how much it is moving. Okay, or the extent of its motion. So what an angular momentum is exactly the same or analogous to this linear momentum. That means when there is a torque or a force acting on a body, that body would have either angular momentum or linear momentum. If a body is really fixed to a point or line, then its motion will be actually measured by the angular momentum. Okay, it is a measure of rotational motion. So angular momentum is a measure of rotational motion. Momentum is a measure of angular motion of any body. Okay, and it is also the rotational analog of linear momentum. Rotational analog of linear momentum. Okay, so we'll see how to define angular momentum. Let us first see this figure. See in this figure you can see there is a rigid body, and and a particle, single particle, we are taking a single particle situated over here on the rigid body itself, and when the rigid body moves or rotates about this z axis, and suppose this point is taken to be the origin, so the rotation vector is this way, along this way, you can see that. And there is a angular momentum acting on this particular, sorry, linear momentum acting on this particle due to the linear force is P. And see this vector, radius vector, and the linear momentum, they make an angle theta. Okay, so this also will be theta, and then we can actually find to see the angular momentum is defined as actually r cross p. It is the moment of linear momentum. It is the moment of linear momentum. So from here you can see nicely, you can derive this formula from here itself. So look here, I'll clean everything. See, look in this figure. R P sine theta, this particular distance. Sorry, this distance. This is r sine theta. R P sine theta is the quantity which is actually called linear momentum. Sorry, angular momentum. So r cross p here. Okay, so this is angular momentum. And see, in this case also, you can use right hand thumb rule to find out the direction of angular momentum, since it is a vector quantity. It is a vector quantity, not here. It is a vector quantity. And what is the relation between torque and, we'll see the relation between torque and angular momentum. Relation between torque and angular momentum. So we know torque means r cross f, and angular momentum we have seen r cross p. Now see, what we can do is we can just take derivative, time derivative of this. So you look here, we assume that the angular momentum remains constant, or you can just take also nothing. So no, angular momentum, yes, let us write from here. So you take this first. So as you do the derivative, once you keep this r like p, and next time you keep the r as it is and take dp dt. Okay, now see, this gives you v cross p, and this gives you, see, this is according to Newton's second law, rate of change of linear momentum is force. Okay, and here see, v and p, they are in the same line, so that's why the cross product would give rise to 0, and you will get r cross f. So this is the torque. So what is torque? Torque is actually denoted by dLdt. So torque is dLdt. Okay, so this is actually the relation between angular momentum and torque. So torque is given by the time derivative of angular momentum. So I'll stop it here for today. With this, we'll take a few numerical example on the next day on this part which I have covered today, like torque, moment of force, principle of moment, angular momentum, relation between angular momentum and torque, and then work done by torque. So on this, I'll take few numerical examples and then I'll proceed further. Okay. So I'll stop it here for today. Okay. Bye for today.